All right, so last time we started into Proton NMR. All right, we talked a little bit about how the signal is generated. The fact that what we're looking at, well, we put the spins in the magnetic field. It splits into different energy levels based upon how those spins are aligned with the applied magnetic field. So for spin 1/2 nuclei like protons or C13, we get 2 energy levels. But all we really observe in our NMR spectrum is the number of spins that are in excess, that are aligned, that are in excess of the ones that are opposed. Okay, because we have slightly more that are at the lower energy state. Okay, and so what we always draw as the signals that we can observe is we draw this vector like this in the plus z direction, and this is really just what we call the net magnetization. Okay, so we've had the plus and the minus, and we canceled out all the ones that are the same, and we just have what's left over. And then what we do is we apply a radio frequency pulse along one axis here, and this can change both the spin populations, and it causes what was called phase coherence. And so it can tip this magnetization into the XY plane, and once it's in the XY plane, this starts to precess around the Z-axis. If we put our detector over here, or we could even just listen to this. Sometimes I put here's our ear. What we'll hear is the sound will change as the direction of that vector changes. So as it comes close to you, it would get louder. As it goes away, it gets quieter. And so it would oscillate. And so from that we get this graph like this. If we take the Fourier transform of that, you get a peak that's at the frequency at which that signal was oscillating. Okay? We talked about that what we see, if we look at the signal, it doesn't look like that, but it decays or it loses its signal over time, and that's because of relaxation. So that signal, once we've perturbed it, we've changed the populations of those energy levels of the spins, and they gradually will go back to equilibrium. There were 2 ways they could go back to equilibrium. One was called T1, and the other one is T2. T1 is essentially losing the signal in the Z direction, so it's just going straight back up into the Z. T2 was the loss of phase, so fanning out around in the XY plane. Okay? The last thing we talked about is just another way to think of this coordinate system is called the rotating frame. I got this new stylus, but it's like every time, it's Bluetooth, every time I start to write, it makes it blurry, and then it comes back in. I don't know if I like this very much. And when I took it to my bigger class, it was super slow, and I couldn't even use it. All right, so the rotating frame, all that says is that the frame, this coordinate system we show, is rotating at the same frequency as the precession. And so it appears to just stand still. Okay, it's just kind of a simplification. So we can look at multiple pulses, and we don't have to imagine it precessing around the coordinate system. All right? So the last thing that I'm going to mention that we talked about was when we talk about how a signal is generated, we drew up what was our pulse sequence, right? And the pulse sequence starts with some delay. I called it, I think, D1. That's a delay. We give it a pulse. So this is our pulse, sometimes called P1. And then we acquire the data. Okay, and so this point here, this is called the acquisition. Okay, and then we repeat that. D1, pulse, acquisition. All right, so that's our pulse sequence. So what we're going to start out by doing today is look at some other simple pulse sequences. Okay, we did talk about that we could also have a 90 degree, or we could have a 180 degree pulse. We could have anything in between. What we're going to do first is we're going to talk about how we would actually measure what is the 90 degree pulse width, okay, on the spectrometer, because that's a value. You know, if you go down and run it, use the NMR, there's a 90 degree pulse width that's already stored in the spectrometer that it would just use. But if you had a important sample and you wanted to run a two-dimensional experiment, you might want to measure this yourself, okay? Or at least we'll know how it is measured. And then we're going to look at two methods to measure the T1 and T2 values. That was the most expensive one I ever bought.
Is it an actual Apple Pen?
No, because I don't think the Apple Pen actually works on this older generation of the iPad. You need a new iPad, too, to go with your new Apple Pen. Oh, okay, so after that, we will then go on and start talking more about spectra. What kind of information can we get from Proton NMR? Okay, and we'll go through each of these and talk about chemical shifts and splitting and all of that. All right? Any questions? This long lead up. Yeah, right. I know we got to get through chemical shifts and splitting before we can do many problems. All right, so let's first look at pulse calibration. All right, and so this is how we would determine the 90 degree pulse. Or a 180, or any of these pulses. So essentially what we're going to do is we're going to run an experiment just like we did before. We start at this point. Whoop. Oh, okay.
Sorry.
I thought it just went out. And what we're going to do is we are just going to vary. We're going to vary what's called the P1. So this equals the pulse width. So we use a high power pulse, and the 90 degree, this pulse width is the amount of time that we apply that pulse. Okay? So if we did this experiment, let's just go up this way, where P1 equals 0, so we essentially did not apply any pulse to that. Let's see, what am I trying to do here? Calibration. What would we get out of it? Nothing, right? Because we've never tipped anything into the XY plane. Okay, so it would still be the same. And if we did our Fourier transform, we just get a flat line, right? We never tipped anything into the xy plane. All right, so let's just say we go to P1 equals, say, 4. I think these are in milliseconds. Okay, and we'll say that, okay, that tips it down a little bit. So there's some, amount of signal in the xy plane. We do the Fourier transform, and we get a small positive signal. Okay? If we do it longer, P1 equals maybe 8. It tips down even farther. Let's say it actually tips all the way down. We do our Fourier transform, and we get a bigger peak. All right, we do it longer. P1 equals 12. It's tipped down to here. And now what are we going to get? We still have some component in the xy plane. So it's going to get smaller, right? This again. If we did it, let's say P1 equals 16. Tips it all the way down into the minus z. What do we get then? Nothing. All right, if we went even longer, P1, I guess I'm going by 4s, equals 20. It would kind of tip, it would go all the way around to over here. Now it has some component in the minus direction. Right, so Fourier transform. Oops, that's not what I wanted. Oops, and we would start to get a negative peak. Right, and it would start to grow negative, and essentially what we're going to be seeing is that this signal is essentially going to oscillate from 0, it's going to get bigger. The maximum signal would be here, okay, where the P1 actually equals the 90-degree pulse. Okay? However, if you're running a series of experiments like that, it's difficult to find exactly the top of the peak, because we said maybe we did this series of experiments and at 8 milliseconds it was the maximum that we saw, but maybe it's really, 8.5, right? We didn't find the top of the peak. Yeah.
And if we have multiple, because we're just showing one peak, but if we have multiple peaks present, like multiple various types of protons, could we increase the height of one while decreasing the height of other?
I think for the 90-degree pulse, I think they should all go down. When we talk about relaxation, they'll all relax at different rates.
But the peak intensities will all stay relative to each other, regardless of P1.
Well, P1, because we're essentially irradiating a wide range of frequencies all at one time. And so we're going to tip them all down the same. Okay, and then they're going to relax at different, they would precess at different frequencies then, and they're going to relax at different rates. But I think they all have roughly the same 90-degree or 180-degree pulse. Because if it wasn't like that, we couldn't manipulate all the spins from the molecule at the same time and do a more complicated experiment. Okay? So the tip where here is difficult to find, right? You'd have to do a really, very fine time gradient to get enough data points to find the top, right? So what would be another way you could do this and instead of finding the top, there would be an easier place to find.
Find where it's at 180 and then divide by 2.
Right, exactly. So it's easier to see when there's no signal than to see when you have the maximum signal. All right, so what we generally do is look for this. We look for the null point, all right, and this is going to be our 180 degree pulse. Right? And then we take that and we divide it by 2. Right? So if we determine this, and this was whichever one, this was P1 equals 16, so we divide that by 2, and our 90 degree pulse width equals 8 milliseconds. You can actually also determine a 360 degree pulse. It would go all the way around, and it would go still look for the null point, and then you divide it by 4. Right? So generally, we determine the 180 degree pulse width, then divide by 2. Okay? So you could you could do this on your own just by going in and changing the P1 value and running a series of experiments. The one thing you have to make sure is that when you do these, that each of the spectra are phased the same, right? Because you can change the phasing, and so even though at one point you have a negative peak, if the spectrometer automatically phases it to positive, then it's going to mess the experiment up.
So don't even manually phase it, just leave it as is?
I think what you can do is get one spectrum that has, say, if you start going from this short, you wouldn't really start with 0, right? And you know that some short pulse width should give a positive peak. And so you'd phase that positive and then try to use the same phasing for the rest of the experiments. So you can either do this one at a time, or the spectrometers now that'll have a special experiment, and you'll tell it, I want to start with this amount of time. This is where I want to start. This is where I want to end in the amount of time, and I want to do X number of increments, right? And then it'll just run all of those, plot them all out together, right? And does it all in one, sequence of experiments. And so, there'll be an experiment on the spectrometer that's for determining the pulse width. Okay? So, knowing the 90 or the 180 is really important, especially once you get into two-dimensional NMR. Okay? If you're just doing one-dimensional, it's not quite as critical. All right? Determining the pulse width, let's look at another pulse sequence to determine the T1 value. Okay, so remember, T1 is relaxation just in the Z direction, like the longitudinal relaxation. All right, and so this is going to be a 2-pulse sequence. So from this diagram, this I value right here, this is the same as what I wrote as D1 before. So this is the pre-acquisition. Why does it keep doing this? It wasn't only the other pen. So there's a pre-acquisition delay. Okay, and the tricky part here, we're determining T1, so we don't know T1, but this pre-acquisition delay actually should be greater than 5 times the T1, right? So you have to make it long enough to make sure that everything is relaxed. All right, and so in order to focus on T1, we want to look at the relaxation when there is no component in the XY plane. Because if we have signal in the XY plane, T2 can also take place. All right, so what we do is we start out with a 180-degree pulse. Okay, so here's our starting point. Let me do that in red, I like that better. We do a 180-degree pulse. And it flips everything into the minus z direction. Okay, so then we're going to wait some amount of time. Okay, so let's do this first. If t equals 0, then what we're going to do is we're going to do another 90-degree pulse. So we're still here in the minus z. Then we do a 90, and it's going to rotate up this way. It's still going clockwise. So we get our signal over here, and then we detect it and do our Fourier transform. Okay, so what kind of a signal should we get? A negative signal, right? All right, so as we increment this tau value, so let's just say tau is greater than 0, what's going to happen is this signal is going to start to decay up towards the plus z. Okay, so then we're going to do our 90. I'm just going to write them together, and then our Fourier transform, and we would get a peak that is smaller in the minus direction. Okay, if we waited even longer, then if we waited long enough, then this signal would start to be going in the plus direction. Then we would do our 90-degree. Oops, I'm running out of space here. 90, then Fourier transform, and what would we get now? It'd be a positive peak, right? So if we look at this series of experiments in the upper right, here's where we started with maybe tau equals to 0, and we have these two strong negative peaks. As we increase tau, they get shorter and shorter, and at some point, it looks like, notice that they're different from one another. This one, here is 0 on the left peak, and the other one is 0 right here.
On the tau is greater than 0 plot, you have the red arrow in the negative z-axis.
Mm-hmm.
Is it supposed to be relaxing up towards the positive z-axis?
Right, so what's going to happen is it's going to tip upside down, and it's going to start relaxing up like this. If we wait long enough, it'll relax like this up through 0 and then relax up to the top. So if we relax just a little and then do the another 90, it'll go into the negative direction. If we let it to relax enough, it'll be right, if we equalize the spins, it'll be right at the like the coordinate, right? If we went long enough, it would be right here, and then we do the 90, then what would happen? Well, if it was only right here,
Zero.
it would be 0, right? And then if we wait long enough, it starts into the positive direction, then we do the 90 and it goes into the plus direction, and then we have a positive signal. Right, so it starts negative, and as we lengthen, negative z, as we lengthen that delay, that tau, then the peaks will start to get smaller and then go through 0 and then grow in to the positive direction.
So when tau equals 0, why? When you have the red arrow in the negative z-axis and then an arrow curving up to it looks like the positive y-axis.
Over to here,
Yeah, what's that?
that would be to the minus y, I think. This is the minus direction, right?
So in that case, it doesn't go through the z-axis, only it goes through.
Well, no, this is showing what takes place when you do the second pulse, the 90-degree pulse.
Okay.
Okay, so we did the 180, inverted the spins like this. We waited here 0 amount of time, so it still looks the same. We do the 90, and that rotates it this way
Okay.
into the minus y, I think, and then we acquire and do our Fourier transform, and so we get this negative peak. Okay? All right, so if we do this series of experiments, like is shown in the upper right, and this is the same kind of thing too, is that when you, after you run the first experiment, say with the tau equals 0, in this case you know the peak should be negative, and you would phase the experiment negative, and you'd have to keep the phasing the same through the series of experiments. Because you don't want, when it starts to go positive, the spectrometer to automatically phase it negative as well. Okay? So what we do then is we graph,
Tau equals 3.
yeah, like this, right? So each one of these lines is with a different tau value.
Yep.
And we have a tau and we have an intensity value for each one of these.
And because we have 2 peaks, you're showing 2 different lines.
Right, and so
Okay.
there's a different line, because notice this one relaxes faster than this one does.
Okay, so it's just for the 2 different species.
Yeah.
Okay.
So in fact, if you had a more complicated spectrum, you could have a different T1 value, a different relaxation rate for each of the signals in the spectrum.
So I was going to ask a question it's on the next slide.
Okay. The intensity of the peak versus, well, we can plot the intensity versus the time delay. Okay, and so like we saw, it starts negative, and then the peaks get bigger. So this red one is getting bigger here. It goes through a 0 point right here. Gosh, this is. And then eventually it maxes out. Okay? That means essentially it's relaxed all the way to the plus z, and we're back to the starting point, and then we're just doing our 90-degree pulse. Right? So it's reached equilibrium again. Notice that this one in the blue is relaxing more slowly. So it took more time to get to the 0 point. It takes more time for it to actually reach equilibrium out there. So each of those is relaxing at a different rate. Another way to do this then is to take that data and plot the log of, gosh, this I0 is the maximum intensity. Right, so that would be out here. And I sub t is the intensity at some time at some time tau versus tau, so the difference in intensity versus some tau, and we get this slopes like this, and T1 equals the slope of this line. Oh, I guess it said it over here. Okay.
What were the red and the blue?
They were just, remember from the previous slide, those were just, I think they correspond to just the two different peaks, two different spins, and they're relaxing at different rates. So they're giving different T1 values. Right, so the slopes are different for each one.
So we run the experiment, we hold tau to be 1 second for one experiment and 4 seconds for another experiment. How do we then have tau be the x-axis if we hold it constant? Like, where do those data points come from?
Well, we ran a whole bunch of experiments, right?
For tau, is this like tau over second? I was just curious about that. What that
Let's,
oh, tau per second.
per
Oh.
second, yeah, okay.
Physical chemists use the division sign to denote units.
Gotcha. That makes sense. Just asking.
Okay. So there's actually, I think this is the way you'd measure this accurately, but there's, I guess there's a fast way to do this too. It's kind of a dirty way to do it, but it's much faster and easier to do it. And so what you actually do is you just say that the T1 value equals the tau at the null point, so that's where it goes through 0. The signal would be 0, divided by the natural log of 2. So this would also be equal to 1.443 times tau at the null point. Okay? So I think this one's not as accurate, but if you needed to know a T1 to know how long you had to have the relaxation delay and that stuff set up in your experiment, this might be a quick way to do that.
And I naught again was, how do we determine that again?
What was which?
I naught.
I naught is the maximum intensity, so
Okay, perfect.
versus the intensity at any specific time. All right. So I'm sure there's a experiment on the spectrometer to do this as well. Yeah, it looks like I'm maxing out my memory here. We have to erase some stuff. All right, the T2 measurement is kind of more complicated. And I'm not really sure the details of how they calculate this or anything, but let's just look at this kind of what happens in this pulse sequence. So to measure T2, they use what's called a spin echo. All right, and so essentially what happens, and having troubles here. So we start in our normal place. I wonder, okay, just a minute. Okay, so we start like we always do. All right, we do a 90-degree pulse. Flips everything into the XY plane. And then, notice here, we do a series of experiments where we do a 180. So the idea here is we wait some amount of time. Some places said, this place said tau over 2, sometimes they just call it tau. I guess tau over 2 means we have one long delay and you're using the equal value on each side of this 180. Okay, so the idea here is that we wait some amount of time, this tau or tau over 2, and we start to get T2 relaxation. Okay, so the signal starts to dephase. Okay, so we could draw it like this. We start to get some dephasing like this. Okay, this is our T2 process. Then what they do is they do a 180 but along the y-axis. So it's going to rotate this way. Okay, and what happens here is we have some of these over here that are faster and some of them over here that are slower. And when we do this 180y, they rotate around that y-axis. But now we flipped it so the faster ones are behind and the slow ones are ahead. So then if we wait tau over 2 again, the fast ones will catch up with the slow ones. And they refocus like this. Okay? And so what happens kind of in this experiment is, so here's the 90-degree pulse here. So we start to get some relaxation based upon T2, or actually what they say is this is based upon T2 star. Then they do the 180 and it refocuses, but then it starts to relax again. Okay, so this is the refocus, and then it starts to relax again by T2 star. And then they keep repeating this 180. So they do another 180, it refocuses, refocus, and then it relaxes by T2 star. All right, so notice as we go longer though, we keep refocusing it, the whole system is kind of relaxing like this as well. So there's another relaxation rate that goes like this, because the refocused ones are getting smaller and smaller. And so in the green, they say that this is the T2 value, and in red, the sharp relaxations are the T2 star. So with this kind of spin echo experiment, the way they're doing it, they say they can separate those two values. But what I don't know here is how you actually take this kind of data and actually calculate the values. I guess at some point along this, maybe you have to change the number of 180s you do and then acquire and then run an experiment or something. Okay, so can separate T2 from T2 star. Remember, T2 star has more of the experimental, the magnetic inhomogeneities and stuff added in. All right, so that's kind of just a rough, dirty picture of at least what this spin echo kind of experiment does. So into the 90, they start to lose phase, then they flip it this way, and then they refocus. And then they start to dephase again, and then they another 180, and they refocus. They start to dephase, they just keep repeating that. But I'm not sure along the way here exactly when they stop acquisition and do a Fourier transform and look at the actual spectrum. All right?
Yeah, because how would you discern T1 from T2 in a plot like that?
Right. Well, I guess it could never, the length of this experiment here could never be longer than T1, right? Because T1 is taking place at the same time, and once it's relaxed by T1, there's no more signal to dephase. So I guess, yeah, this amount of time's got to be short on the order of T1 at least. All right, so here's comments about these. Remember, we talked about, for one, that T2 or T2 star has to be shorter than or equal to T1, because once T1's relaxed all the way, there's no signal left to dephase. Okay? T1 is what limits how fast we can pulse, right? Because we need to have to get complete relaxation, we should do 5 times the T1 value. Okay, this allows all the signal to get back into the plus Z, into its equilibrium position before we pulse again. Okay? T2 influences the peak shape. And the way I think about it is if there was no T2, it would stay perfectly for a given signal, it would stay perfectly in phase, and we get a very sharp line, right? Because every spin for a given nucleus would have exactly the same frequency, right? But if we're getting T2 relaxation, then for a given signal, the frequencies are spreading out. And so when we do our Fourier transform, when we see a peak, we're actually seeing an overlapping of a whole bunch of different peaks, which ends up giving us a broad peak. So here's kind of what it shows is here, if our FID is very long, so there's slow relaxation, then this leads to sharp peaks. And look at this one here, it's a very fast relaxation, and this ends up leading to very broad peaks.
So that's why you change your relaxation time?
No, I think what this means is that on the fast one is there's probably something else in there that's causing it to relax quickly. You know,
shorten the time, and so that way, that 0.1 where it's actually occurring, you can make that your total time of sampling.
yeah, but I think that it's not that you're not acquiring a long enough signal, enough data points. It's that it's relaxing so fast. It's like the spins are dephasing so fast that we're ending up with, each signal is like a composite of a bunch of different frequencies. This is essentially why you get in that paramagnetic NMR, because it relaxes very fast, you end up getting very broad lines.
Yeah, and we just change, the papers I've read changes the relaxation rates to just be much faster. Like the pulse time or the...
Well, I think by changing the pulse width or even the acquisition time doesn't change the process of relaxation, right? It just changes how you're sampling that signal, right? So to get sharper lines, you actually need a slower relaxation process. You know, in fact, and I don't know, when you guys run NMRs down there, it probably never has a step. Do you watch the FID acquire?
You can, if
You
you
can't-
set it a certain way.
Right, because I know, you know, when I used to, you'd always see the FID, and sometimes it would be very long if the shimming was very good. You know, you could have a very nice long FID, but one time you go down in there and the shimming's crappy or something, and then you see it's relaxing really fast, and then you end up with a terrible looking spectrum, right? It's all broad and everything. So the other part of this is, and we kind of mentioned this before, is that this difference in frequency at the half height of the peak equals or is related to 1 over the T2 value. Okay? And so if if T2 is long, then that gives us a very small number. Okay? So it's kind of a practical thing. All right, everybody with me? Okay, so I inserted in here, oh. That's what we already did. And that's what we already did. Oh, this is what I kind of inserted in here. This is an online book that's kind of interesting. Here, let's go back. I think I can. Go back. So here's like the table of contents over here. And it goes into a lot more detail. Well, it doesn't, it goes into a lot more topics than we do. But one thing that's kind of interesting, most of these they don't go into a ton of detail about it. But if we like click on spin, oh, I think I couldn't get this to work on here. Okay, let's go.
Did you put a link to this in the Canvas?
Oh, yeah, that'd be nice.
Yeah, under the links I can put it in there. But what you can do is if you go, you know, over spins, and this is a lot of the stuff that we've looked at, and I don't think that this is exactly going to work, but these little icons over here, let's see. On the computer, if you click on those, like the little triangles, it'll show a kind of a animation of a spin that's.
One dot has it on his computer.
Huh?
One dot has it up on his computer.
Oh, yeah. So, yeah, see, so if you click on one of those, it'll show how the spin is being manipulated and stuff. So it's kind of an interesting place to go and look at some of those. All right. Okay, so enough of kind of general theory for us. You know, what we'd like to do now is start to think about what kind of information we can gather from NMR. Okay, so if we look at this simple spectrum, what can we get out of this? What parts of this give us information?
Super clean.
Huh?
Super clean.
Yeah. It's not very interesting though either, right? What is it?
Give it 3 to 1 maybe.
Probably if you run very much NMR in the lab, it's probably a common contaminant.
Oh, velocity?
Yeah, ethyl acetate, right?
Yeah, that shows up all the time.
Oh, yeah, I see.
No,
Oh, yeah.
My
My stuff is
methoxy
super
peak
clean.
is at 3.9, and so that's how I know I'm at the end of my methoxy peak, so I'm on some substituents.
Yeah. Yeah. Okay, so if we look at the spectrum though, what parts of the spectrum give us information? Yeah.
So quick, what's
3.
water usually shows up between 2 and 2 point something, and sometimes that 2.4 gets smushed with the water. What solvent is this in, and do we?
Well, it depends where where the water peak depends on what solvent you're in,
Okay.
right? So usually, if you're in chloroform, deuterated chloroform, then the water peak is at 1.5 or something like that. So
Not good.
that would be down here, but this is a super concentrated sample,
Okay.
and I'm sure they ran it so they didn't have those kind of impurities in there. Yeah. Yeah, we'll talk about that later, choosing solvents, and because sometimes, especially if you have very weak samples, low concentration, then it's important to choose a solvent that can move that water peak out of the way so it doesn't overlap with signals that you're interested in. Okay, so back to the question. So what parts of this spectrum can we gather information from?
So are you asking in terms of without knowing, like splitting or integration?
Well, splitting is
That is
one,
what we get, but.
right? So splitting is one thing that we can get information from,
Integration.
right? Integration.
Relative peak heights usually.
Well, it's not so much the peak height, but it's this integration. It's the area under the peak. Because the peak height can change for an equal integration, right? Just depending on whether it's sharp or whether it's broad.
Shifts.
Yep, and then chemical shifts.
And those curves, I forget how to read them.
Yeah, so we'll talk about that in just a second
I
here.
just turn them off because I forget.
Well, yeah, so we're going to talk first about integration, and then we're going to talk about chemical shifts, and then we're going to talk about splitting. And along the way, we're also, another thing that gives us some information is just the number of peaks as well, right? All right, so let's integration. Okay, so integration measures the area under the peak. And for proton NMR, that area is proportional to the relative number of hydrogens. Okay, it doesn't give us the absolute value, but it gives us a relative value. So we see here, that if we measured these, we took out our ruler and measured them, we'd get some number in centimeters or something, but what we'd find is it should be roughly a 2 to 3 to 3 ratio. Usually if I was doing this, I would measure it and you try to set one of the values to 1, right? But in this case, it doesn't work, and so you'd find that it's a 2 to 3 ratio, okay? Most spectrometers now will actually give you a number, all right? And so I'm sure downstairs, and you could set one of those numbers at 1 if you wanted to, and everything would be relative to that, or you can just read them off, okay? But the main thing is that these integration lines, this distance is proportional to the relative number of hydrogens under that signal, okay? So one of the things that you have to be careful of when you're doing this is both if you were doing it manually and or if you're asking the instrument to do it, is you have to make sure that these integration lines are nice and flat like this, okay? Because it's only this part in the, in the middle here, the signal should only be this height here, right? And if this part is before the peak and this part is after, if there's no signal there, then those should be flat, right? And so we would just measure some distance from here to here and measure this, okay? But sometimes it's not so easy. Sometimes you end up with an integrations that look like this, right? Or sometimes you have integrations that look like this, right? And so there are some parameters that you can go in to adjust the integration lines, and so they can be adjusted to look like this.
So that's what when you pick the 2 points that you're gonna integrate from, that's what the curve helps you with, is to figure out where there actually is signal, where there's no signal, because when it goes flat.
Right. So yeah, when you're doing it, you're setting up the integration lines. You are usually telling the instrument where to start and where to stop, right? But notice if this is how the integration looked, right? Would this give a correct integration? No, this would give an integration that's too big, right? Because you really want to start at the inflection point here and go to here. Or what about this other one? Yeah, so this one would be from this point to this point. This would be actually measuring this distance, and this is too small, right? And this one is going from the top, from here, clear up to here, and so this one's too big, right? Too big.
So this is why the phasing is also very important.
Right, if you want a good measure of integration, you either need to adjust, and I can't remember exactly what they call those, the pitch and the roll or something like
that. And the one.
Hmm?
Like the 0 order and the first order.
Maybe on the integrations. Because one will tilt, maybe it's the tilt, one will tilt the whole thing like this, and one will cause it to bend over, and make the curves more.
Is one just the frequency and one just...
I
Casey
don't
kind of
know.
explained it.
Okay,
Sorry.
yeah. So if the integration wasn't looking so good, like one like this or this, what could you maybe do other than adjust the whole thing to get a more appropriate or a better integration value?
Besides doing the adjust phase,
Yeah.
you could pick different spots to start from.
Right, you could start, instead of starting way over here, you could cut it right at the inflection point from here to here, right? And then you get a much better value. Or on this one, you could cut it from here to here.
Would running more scans help?
Not well.
Because you clean up the baseline by removing some of the noise by increasing...
Right, the noise itself, though, should cancel out.
Even in 16 scans.
Yeah,
Usually.
it should. So where there's no signal, it should still be flat on the integration, even if it's noisy.
So maybe concentrate your sample more.
Well, I think it's just a matter of adjusting these integration lines. Yeah, so that's just some stuff that we have to pay attention to. And so, the other thing to just make sure that you remember is it's the relative. We could have the same spectrum if it was some molecule that was symmetrical, and even though we have a 2 to 3 to 3 ratio, it could actually be 4 to 6 to 6, right? Or 6 to 9 to 9, right? So it's just giving the relative ratios. All right, so what about chemical shift? So before, we already talked about how the frequency of the precession is equal to this gamma times B0. B0 was the applied magnetic field over 2 pi. So if this is true, why do different protons have different chemical shifts? Right? Because this looks like a bulk thing. If all protons are only related to gamma B0, then they should all be the same. Right? And
they feel different magnetic fields.
right. It's because, essentially, because the electrons in the molecule, we're looking at the nuclear spins, the protons, but the electrons around signals create their own little magnetic fields, right? And those magnetic fields generally oppose the applied magnetic field. So it shields or subtracts part of the magnetic field that the proton is experiencing. All right, so we could also write this out like this. So the effective frequency, so this is the frequency of the actual light, equals gamma B0 over 2 pi times some factor, 1 minus sigma, and this is called the shielding constant. Okay, and the shielding constant is related to this local magnetic field. Okay, so the local one is the result of electrons near the protons.
So is B local equal to sigma?
Not exactly, but they kind of go together a little bit here. I don't know how to calculate the sigma, but the way to think about it is B0, this is the applied magnetic field, the magnet. The local, B local, is the magnetic field that's created by the electron density. Okay, and that electron density, essentially what we have is something like this. Okay, so here is B0. This is the amount of magnetic field that's applied. Okay, B local opposes B0. So this is B local, and it essentially subtracts or shields the nucleus from part of that magnetic field. Okay, so this is B effective, and this is what the proton is experiencing. And so if each different proton that we're observing has a different environment, it's going to have a different B local, and so it's going to feel a different B effective, giving it a different frequency. Okay, so yeah.
Sorry, so, how do I explain this? So would you say B effective, should that replace B not, or?
Well, I think B effective is, the way I would think about it is B effective is what a given proton, that's the magnetic field it's actually experiencing, because it's kind of shielded by this B local.
So how does I guess, if you're trying to, say, calculate it,
Mm-hmm.
how would you take that, so you would take that, because you have the shielding constant.
Right.
Is that just what you'd be using to calculate it in a way, or?
I think that this is going to be all more empirical.
More empirical.
Yeah, so, the bottom is kind of a hand-waving thing. We know that something influences it, and so each frequency is going to be slightly different.
Okay.
Do our books contain the sigma values, or are they?
No, I don't think so. Not in a calculation type of fashion.
And are they unique to each system, or is it universal for?
Well, they're going to be unique to protons in some unique environment.
Compound to compound.
Yeah, well, and signal to
Sideways.
signal, right? You can say, okay, a methoxy group is going to have a similar B local, similar this shielding constant, no matter what molecule it's in, right? Methoxy groups have about the same frequency, same chemical shift.
So that's how we can kind of say if we add a electron-electron group or add a chlorine to something, we can see it be shielded or de-shielded.
Right.
It's coming from.
Yeah, right. So this is going to be more of a qualitative thing.
Okay.
So this B local, though, depends upon the electron density. Okay? So there's three different things that can influence B local. One is the electronegativity of adjacent atoms. One is what's called diamagnetic anisotropy, is kind of ring currents, pi systems. And another one is the amount of substitution, whether it's primary, secondary, tertiary, this kind of thing. All right, so before we get to look at the actual chemical shifts, we have to know what kind of scale we use, okay? Because this frequency that we're going to observe depends upon the magnetic field, right? And therefore, the frequency, the chemical shift, the frequency would end up being different on every different magnetic field, every different instrument, right? If you went and you looked at one on the 300 megahertz NMR, it would have a different frequency for a signal than on the 500 megahertz NMR, right? So what we have to do is use this relative scale, okay? And this is referred to as the delta scale, and this is in parts per million, okay? So this is calculated based upon the difference in the frequency. This is the frequency. This difference is the frequency of a given peak from our reference. Okay, so it's a relative distance. And we're going to divide this by frequency 0, and this is going to be in megahertz. This is the frequency at B0. Okay, so 200 megahertz, 300 megahertz, 400. That's of the magnet. All right. So what do we use as our reference?
TMS or solvent.
Yeah. So the usual reference for proton NMR equals TMS. So trimethyl silane.
But you still, that TMS is still referenced to residual solvent, or when you use TMS, do you just simply make it relative to TMS?
Yeah, so usually, so the point is, so we don't always add TMS to our samples to adjust the chemical shift. However, and what we do is we oftentimes, well, we typically use what's called the residual. What is the residual solvent?
It's the part of the deuterated solvent that we use that isn't deuterated.
Right. So usually, for example, our solvent is CdCl3. Okay, but it's only maybe 99.9, let's just say 99.9% deuterated. And it has CHCl3 at 0.1%. Okay, so what we usually do is we reference to this residual amount of proton. However, the value that we put for that is relative to TMS. Somebody else has done that experiment.
So that's why we put 7.26.
Right.
Yeah.
Because if
We
you...
were having that issue before.
Yeah, because it shows up as 7.24 if you do it relative to TMS, but if you do residual solvent peak, apparently it's 7.26.
We had that issue with me. I'll have to double check. We'll need to double
Yeah,
check
we'll do
that.
the same.
You know, it's funny how that seems to have changed a little bit, because when I was first doing it, we always used to set it at 7.24.
Yeah.
But
that's
then
what I did.
some other
Yeah.
reference books
Yeah,
now
In
say
2010,
7.26.
Yeah, they started publishing this in 2009. They started
Some-
switching.
Yeah, right.
Yeah, when I was doing stuff before, I was like 7.24. And then
Mhm.
I started doing that, and Steven pointed out to me, oh, it's 7.2. So I'm like, what?
Right.
So,
That-
Yeah,
I don't think that should be relative to whether what your reference is, though. The 7.26 should be relative to TMS.
See, because acetone does, acetonitrile does the same thing, it seems like.
Well,
Because our
let's
instrument
double
shows it at
check
1.9.
Yeah, I think it's just the accepted value has changed.
Okay.
we'll double check.
All right, so let's finish about this scale, and then we'll be done. Okay, so at different magnetic frequencies, or frequencies that are at different magnetic fields, what we end up with is that if we start with 0 over here, then the number of hertz increases faster if we have a higher magnetic field. So at 300 megahertz, the way we usually do this is this would be, say, 300, 600, 900, 1200, like this. Okay, and so, for example, if we had a peak that was at 600 these are in hertz. If this was at, here's our signal at 600 hertz, we divide it by 300 megahertz, and we call this 2.0 parts per million, because it's hertz per megahertz. Okay? If we ran this same sample at 600 megahertz, then the spectrum goes like this. This is 600, this is 1200, 1800, like this, and that same peak would be right here. Right? And so then we have 1200 hertz divided by 600 megahertz. So this is still at 2.0 parts per million. All right, so the higher the field, the more hertz there are per part per million. Okay? And so this is how because we're always dividing by this, the magnetic field, we're kind of standardizing our scale. And so we should get the same chemical shift no matter what magnetic field strength we use. Okay? All right, so let's stop there. We'll talk about next time about chemical shift, and then we'll start into splitting, and then pretty soon we'll be ready to start working some problems. Okay?
And the problem sets